All right. So last week we started discussing our chemical bonds. So we'll just go back and do a wee bit of review. We have three primary types of chemical bonds. We have the type of chemical bond where we are sharing electrons. Sharing is caring, caring is covalent. We have an ion. Remember, the definition of an ion simply is something that has gained or lost an electron. If I gain an electron, I'm taking on negative things, I become more negative. If I am releasing negative things, I'm becoming more positive. Opposites attract, and we have this electrostatic bond, and that's going to be our ionic, pertaining to ions. And then finally, we have our hydrogen bond, because remember, electrons are in a cloud. And sometimes the cloud can accumulate more in one area than another. And that can cause what we call a polarity. Polar means a difference in charges. So I might have one area of the molecule being a little bit more positive and one area of the molecule a little bit more negative. And then that's going to allow that weak electrostatic, very similar to our ion, although we haven't changed any electrons with our hydrogen bond. We're just using the differences in the charges. So sharing is caring, caring is covalent. We can share more than one electron. We can share 1, 2, 3 electrons. And so that would be our single, double, and triple covalent bond. And again, we can share them equally, where we don't have any difference in the charges. Everyone is the same. Or we can share them unequally, which gives us polar. And remember, the word polar just means a difference in charges. Non-polar means no difference in charges. So here we had an example of creating the poles. So this is what I mean by one area is a little bit of a different charge. If we see here, we got a lot of electrons that are gathered on this side and not a whole lot gathered on this side. And so what that means is that well, actually, technically, we've got no electrons gathered down here. They're all gathered right here. And so what that means is this area is going to be more negative, and this area is going to be more positive. So right here, you can see. Our ionic bonds, again, electrostatic. We're going to be gaining or losing an electron. Here we have the primary example that we have, and I do not have my chat turned on because I'm just on my single laptop. I don't have my big computer massive setup. So if you do have a question, don't type it, just unmute yourselves and ask. All right.
Well,
so
I was just telling you, I'm sorry I'm late. Someone was breaking into the water bars in my complex. My camera's off because I'm waiting for the police outside.
Oh my gosh, Charles. Okay, I got you. No worries. You do what you got to do. Holy smokes. All right, so here we have our prime example of sodium. And we know that sodium has one sad, lonely, pitiful little electron out here in space all by himself. And this molecule, this element, sodium, the purpose, their whole being is to be whole, to have that outer shell be whole. And it's much easier for sodium to flick out that one sad electron than to go and try and pick up 7 others. And so our sodium is going to donate and get rid of that electron, making the next shell whole. Chloride, on the other hand, has 7 in the outside ring. And so he can go out and pick up that donated electron, and now he is whole. But sodium has turned more positive because we got rid of an electron. Chloride has become more negative because we picked up that electron. And now we have opposites attract. This is just another picture. We went over that on Friday. We have the two, this is just definitions, guys. This all I want you to know is that cation is an ion that has gotten rid of an electron and has a positive charge. cats make me positive. I think, I don't remember, it might have been Sean that said, remember it because the letter T looks like a positive. And so that helps you to remember that a cat ion is a positive. We've gotten rid of a negative electron. And then our anion is a negative charge, and they have picked up an electron. And I think, yeah, up north, the way we say this is a cation and an anion, but nobody had any idea what I was talking about. So I just used the American vernacular now. I was teaching this class and I was all like, oh, that's cation and this anion. And they're like, Miss Huff, are you saying onion? What is happening? No, anion. So it's cation and anion. And then finally, just to review our hydrogen bonds, remember, are kind of a combination. We have oxygen and hydrogen pre-bonded together into a molecule. And then that molecule has a positive and a negative area, and that allows it to bond via electrostatic to other molecules. So our hydrogen bond really is kind of a combination of both. We're both sharing electrons because our oxygen and our hydrogen are covalently bonded, and we have the electrostatic molecules bonding to other molecules. So here we have our H2O molecule, and we can see it is polar. Polar by definition, difference in charges. We have our negative, we have our positive, and we know that opposites attract. So the positive in this molecule will be very loosely and very weakly attached. Here's positive again, very loosely and weakly attached. Here's our positive and our negative. And this very weak attachment is what gives water its kind of slippery properties, that it can maintain itself in any of the three states of matter: solid, liquid, or gas. And in fact, I was watching a video. I don't even remember what I was doing over the weekend. It was one of those bizarre rabbit holes I tend to go down, where there is in fact a state of water where it can be in all three states simultaneously. It was pretty cool. It was pretty cool, where it was freezing, boiling, and steaming at the same time. I don't
Can
know
you
how.
repeat that? You froze on us.
Oh dear, okay. So here we have our hydrogen bonds. And so we have the area, because remember, this is polar, polar meaning difference in charges. Here we have our little positive area where we don't have any electrons gathering. Here we have our negative area where we have all of the electrons gathering, and the opposites attract, electrostatic, very weak bond. It is this very weak bond that allows water to be found in all three states of matter. And I was saying, I went down this weird rabbit hole over the weekend, and there is a very rare state, though, that water can appear in all three states simultaneously. It was pretty cool. It was a pretty cool, I think it was a YouTube video probably. And this little bowl of water was freezing and boiling and steaming at the same time. So it was in fact in all three states simultaneously. It was really pretty cool. So, all right, so now we're into new material and chemical reactions. Now, let's just take a step back, because I know some of you are in tears, fetal position. I told you all about my horror story when I had to take chemistry and I got a negative grade. Probably the first college student in history that got a negative grade in a class. He was a terrible, terrible teacher. He was awful. What we are going to be doing, my darlings, definitions. Definitions only. We are going to simply define the different types of reactions. I will not be having you solve the equations. So if you've ever taken any kind of basic chemistry class, you know that we do have, it's almost like a mathematical equation. 2 + 2 = 4. Same thing here. I have x + y = z. So this is no different than a mathematical 2 + 2 = 4. Except here, these are what are reacting together. I'm taking one, I'm taking the other, I'm adding them together, I'm bippity boppity boop, and it creates something new. So these are called my reactants, meaning they are reacting with each other to produce something new, the product. You can also think of it like the analogy of baking a cake. The reactants, the things that I need to react together, I have my flour and my sugar and my shortening, etc. Separately, those are all just ingredients. But if I put them in a bowl and I mix them all together and I apply heat, those ingredients then react with each other to produce a cake, the product. The arrow is going to tell us which direction. Are we taking the ingredients and making a cake? Or are we taking the cake and breaking it down to its ingredients? And so that would be determined by what direction is this arrow going. That's the depth we're going to go, you guys. Don't panic. I'll just give you guys a minute. You're all furiously writing. What a gloomy day it is today.
Right?
It's just, it was so foggy. I hate daylight savings. This is the stupidest thing ever. Hate it. But Miss Huff,
Yeah,
I
I
didn't
woke
really
up
feel-
with my kids out of school. I got to sleep a little bit later this morning, but I was like, why is it still dark? Like, why
I
is it still
hate it.
dark?
I hate it. Hate it, hate it, hate it. It's no reason to be doing it. Should be abolished. When I become president of the world, that's the first thing that's gonna go.
But which way would you make it darker an hour earlier or keep it lighter an hour?
You know, I'm on the fence. I think I would make it, I think I would keep it lighter later. Because if I'm president of the world, I have no reason that I have to get up early anymore. And so I would rather, you know, have it light a little bit later into the evening and keep it dark in the morning because I'm going to be sleeping in. I'm president of the whole world.
I think you'll be the last person to ever get to sleep because you're president of the world. I don't think you'll even get to sleep.
Oh, no, I would, because you delegate. You just get the people in who are good at what they do and you delegate stuff. It'll be fine. All right, so we have 3 different kinds of reactions. We have a reaction where we're making something. We have a reaction where we're destroying something. And we have a reaction where we're both making and destroying something. That's it. Those are the 3 reactions. To make something, to create a new thing, is the term, the medical term for that is synthesis. If you are synthesizing stuff, it means your body is creating it. So a synthesis reaction is going to be creating something new. Think about all the other words that use synthesis, like photosynthesis, the creation of plant energy. So synthesis, by definition, is just where we are putting ingredients together, making something new. Decomposition, well, I always just think of a dead body when I hear that word, to decomp. And so to decompose, you are breaking something down into its most basic structures.
Sorry,
So-
Miss Huff, you froze earlier. We couldn't hear.
Okay. I do not know what's happening to my internet right now. To synthesize means to create something. If you think of like photosynthesis, the creation of plant energy. So to synthesize is where I take my ingredients and I am making something new. Decomposition, I think of it like a dead body or a compost heap where you have things being broken down. So a decomposition reaction is I am taking the thing like the cake and I'm now breaking it down into its ingredients. And then exchange is just a combination of the two. I am first breaking down so that I can create something new. And so here again, I'm not going to have you solving these equations for any kind of test, but this does kind of show you here synthesis, creating, we're baking the cake. So we have our ingredients, we have our arrow showing x plus y equals xy. So flour plus sugar equals flour sugar cake. Decomposition, we just go the other way. Here we have our cake xy, and we are breaking it down into its ingredients. And then our exchange is just that. Here I've got two products, W, X, Y, and Z. And what I'm going to do is I'm going to break apart both of these and I'm going to swap them. So now I have W, Y, X, and Z. Now my synthesis to create something takes energy, right? It takes energy to bake a cake. Decomposition, well, what happens when we break a bond? Pew! We release energy. So synthesis, we need energy. Decomposition, we're releasing energy. And then in our exchange, we don't have anything happening because they cancel each other out. The bond breaking provides the energy needed to make something new. And those are the three definitions of our chemical reactions. So I'll give you guys a memento. Let me know when you're ready. Oh, Faith, just give him the toy. Oh, that's funny. All right, so we're gonna go ahead and.
Can you erase some of the drawings?
My dog just attacked my mom. I gotta go.
Okay. Here you go, Sean. How's that?
Thank you.
You're very welcome. I'm looking at Morgan. She looks very canine today. She's a shapeshifter. All right, so we're gonna move on. So I got a little ahead of myself here. So with our synthesis reaction, it does require energy. Our decomposition releases energy, and then our exchange is a combination of the two. The energy that we release is used for our synthesis. So this is just, are we releasing energy? Are we needing energy, or are we canceling each other out? So what sort of factors are going to affect our reactions? Well, the concentration of the reactants, the more of something you add, the more effect it's going to have on the creation of a product. I mean, we've probably all seen, although I don't know if you've ever, this kind of a fun rabbit hole to go down on YouTube, is where you have like these high school science teachers who don't measure out the chemical ingredients for the experiment that they're doing correctly, and they end up blowing something up. It's really very funny. So the concentration of the reactants can influence the rate. And then of course, temperature. The application of heat will usually speed up a reaction, and the absence of heat, if we make it colder, will slow down a reaction. So those are the two main factors that influence these rates, the concentration and the temperature. Now, the activation energy, again, don't get bogged down in the details. This is just definitions that we're discussing here. The activation energy is simply exactly what it sounds like. What kind of energy we need for something to happen. That's it. And then we do have some things that will help to turn reactions on and off. For example, in our bodies, everything about our bodies anatomically is nothing but reactions, chemical reactions happening in an instantaneous, just astronomically mind-blowing scale. So what turns these reactions on and off? Well, we have things like enzymes. Enzymes are basically just a word for turn something on, turn something off. Think of like if you take your finger and you flick the light switch on, flick it off, your finger is now working like an enzyme. And we have these enzymes all through our body, and these enzymes are specific for a reaction. It's almost like a lock and key. The enzyme will only initiate the reaction it's supposed to initiate, and then turn it off when it's supposed to turn it off. So here we're just going to go over some of our organic and inorganic compounds. Now, there's a lot of material here. I am going to just kind of give you the highlights. Why am I going to do that? Because the organic and inorganic compounds, for the most part, equal nutrients. Carbohydrates, which are sugars, fats, which are fatty acids, proteins, which are amino acids. We have our inorganic, which is water and vitamins and minerals. We are going to be covering these in great detail next term in nutrition class. So right now I'm just going to do a handshake, how do you do, introduction into these. So the definition inorganic means they do not have a hydrocarbon backbone. I have a picture to show you here in a second. Organic compounds do have a hydrocarbon backbone. And the organic compounds have to be broken down into their most basic molecular structure in order for our bodies to use them. Think about with our organic compounds, they are created with Legos. Okay, what can you make with a Lego? You can make anything with a Lego. And I have some Legos that are specific to make sugars, some that are specific to make proteins. But when you eat the Chipotle burrito, that's essentially alien material. Your body doesn't understand, what is this thing coming into me? And so what your body has to do is take the chicken, let's just take the chicken in the chicken Chipotle burrito, takes the chicken and has to break apart the Legos. In order for me to build and use those Legos, I got to first break them out of what they're already built into, which is the chicken protein. So my body breaks apart the chicken, separates out all of the Legos, and then shoves all of the loose Legos into my circulation where they can travel and go to the places where I need to reassemble them into other structures. Same thing happens with sugars, the same thing happens with fats. And so our organic compounds have to be broken down in our bodies, where the inorganics are really already in a structure that our bodies can use. So again, I know there's a lot of words on this slide. Don't panic. Don't panic. In fact, just sit back for a minute and just listen. So water is what we call the universal solvent. What do I mean by that? You can literally add anything to water. Okay, let me click now. You can literally add almost anything to water. We have areas that are hydrophilic, hydro meaning water. Phil is affinity or love. Hydrophilic, I love water. And you have hydrophobic, I am afraid or I repel water. So where do we use water in our bodies? Well, we are water-based beings. About greater than 60% of our entire makeup comes from water. Think about not just like your tears and your snot and your saliva and your sweat, but every other structure. You have the jelly substance, the cytosol inside the cell, water-based. Your blood, water-based. Your literally everything about you, water-based. And how do we lose it? Well, we're leaking water pretty much all of the time. Humans are disgusting. I'm just saying, humans are so gross. And we are leaking oils, and we're leaking sweat, and we're leaking just all of the things. We lose water primarily by our urination, our urogenital system, kidneys, bladder. And the thing is about water is, again, it's kind of this magical property. It's very easily able to absorb heat, but it doesn't evaporate very easily. So I put a bowl or a pot of water on the stove. I can have it absorb heat to the point where it's even boiling and turning into steam. However, it's going to take a very, very long time for that water, that entire pot of water, to completely evaporate. And that's kind of the whole premise behind the water, is that although, yes, it does absorb energy and heat easily, it does not evaporate easily. And then, of course, we use it as lubrication. All of your mucous membranes. Think about how, if you've ever had dry eyes. I don't know, did I freeze up for a minute there? So think about if you've ever had dry eyes, how uncomfortable that is. Well, every time you blink, you have tears that lubricate. You've got saliva lubricating. You have mucus in your sinuses lubricating. You even have oil that is lubricating your joints, your freely movable joints. And all of that's because of water. So the big things to take away from this slide, so universal solvent, know the definition, hydrophilic, hydrophobic. It's easily able to absorb heat, but it does not evaporate easily. Those are the big things to take away from this slide.
Hydrophilic is they do not evaporate well.
I'm sorry, Alondra, I didn't get that.
Hydrophilic is that it takes a while to evaporate.
No, hydrophilic is where it is water loving, that it is got an affinity for water. Hydrophobic means it repels. Let me give you an example of hydrophobic. You cook the chicken and the chicken fat is in the pan. Chicken fat is hydrophobic. So when you put the water in the pan, what happens to the fat? It globs up together and it repels the water. That would be hydrophobic. Hydrophilic is where we mix very easily and we are water loving. These two words, hydrophilic and hydrophobic, are going to get important in our next chapter when we start talking about the cell membrane. The cell membrane is like the skin of your cell. And the hydrophilic, hydrophobic properties regulate what is allowed to come in and out of your cells, because we don't want there to just be free passage of stuff in and out of your cells. We've got stuff that we need to keep in there, and we got stuff we need to keep out. And so the water loving, water hating, those kind of help to regulate stuff going in and out of the cells. All right, so salts. We've already talked about one specific salt.
Can you go back real quick, please?
Of course I can, yes. Absolutely, excuse me. So I'm just going to talk about salts while we're still on this slide. So salts are like the one we talked about, sodium, chloride, but salts are really just, there's a lot of different components to them. Let me know when you're ready.
I'm ready, thank you.
Fabulous. So salts are predominantly going to have an ionic bond. And remember, ionic, gain, lost an electron, and then bonded by electrostatic. And the primary one that our body uses is going to be sodium and chloride. And in fact, our body's ability to regulate the amount of water that we keep or lose has everything to do with sodium. Sodium is a big factor in our kidneys and the function of our kidneys. In fact, the inside of our nephron, which is the functional cell of our kidney, is super, super salty. It dips down into the middle of the kidney and it has this super salty environment, which promotes the movement of water. And so salts are really just going to be the principal mineral and stored really throughout the body. Our body stores a lot of these salts in order to repurpose them. They also transmit an electrical charge. This is going to be important when we start talking about things like the neuron, which is your nerve cell. We have sodium and potassium, which are able to conduct a charge and change their charges. So we're going to talk about how they can change their environment's charge and why does that help to transmit an impulse to another neuron cell. But for right now, all we need to know is salts have ionic bonds, electrostatic, and they have the ability to change their charges, transmit an electrical charge. That's it. So ionic bonds, electrical charge. So acids and bases, these are really referring to what we call pH, which is just how acidic or how basic is something in your body. We're really not going to be touching too much on acids and bases. You're going to get into this when you get into clinical pathology and canine clinical management in your second semester. Because we have things that we can introduce into the body. If the body's pH is too acidic, we have things we can introduce to neutralize the environment. Same thing if it's too basic, we have things that can acidify the environment. And these are also known, here's a word, electrolytes. Electro meaning electricity. Electrolytes are just something that can carry a charge. So honestly, as you're reading through this, I'm probably not going to really test you too much over anything on this slide. I just need you to have heard the word electrolytes before, because we're going to be using that word quite a bit. In fact, you've probably heard it if you're drinking those Monster drinks, or you're drinking the energy drinks or the replenishing drinks. They're fortified with electrolytes. Well, electrolytes just carry a charge, and they can help to stabilize other reactions in your body.
So is that anything that can transmit an electrical charge? It's not just the salts?
So in this case, an electrolyte is literally anything that can transmit a charge. And in this case, we're referring to specifically acids and bases.
Thank you.
Here's the pH scale. I know this picture's a
Can you go
little bit
back real
hard to.
quick, please?
Yeah, I can go back, no worries. So the pH scale,
Okay, that's good. Thank you.
no worries. We're going to be using this. We can check the blood pH. We can check the urinary pH. See if we have an environment that is favorable for certain conditions to happen in. The smaller the number, the more acidic we are. The larger the number, the more basic we are. So here we have a very small number 1 and 2. Our gastric juices, our stomach juices, are about a 1.5. Super acidic. They are literally like hydrochloric acid. And here you can see very, very basic. The bigger the number, the more basic it is. So here we have oven cleaner, household ammonia. Our blood is just a little bit more basic than neutral. In fact, our blood pH is usually on average about 7.4. So just a little more basic than neutral. And so what do we need to take away from this? Just the very generalities of the scale. The smaller the number, the more acidic. The larger the number, the more basic. And then we have something called a buffer. And what a buffer is, if you think about, okay, so if you and another person are starting to get into an argument, you're starting to really interact with each other, and you have somebody come in the middle and go, whoa, 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 you guys need to separate. You guys need to just neutralize. That's a buffer. That's all a buffer does, is it minimizes the ability to change. So the buffer is going to help to neutralize the acidic. Let me give you a true life example. I'll give you a couple.
Miss Huff, can you go back real quick for the last slide? Thank you. That's all.
Yep. So the smaller the number, the more acidic. The larger the number, the more basic. And as I said, our stomach acid is like hydrochloric acid. It's a very small number. It's like 1.5. So you have eaten something, and your stomach is producing a lot of acid. And that acid is now burbling and gurgling up into your esophagus. And your esophagus is not protected like your stomach is. And so what happens to you when you get stomach acid burbling and gurgling into your esophagus?
Heartburn?
Heartburn.
Heartburn. And it's
This
called
morning.
heartburn because the opening, I know we're always like, oh man, my stomach hurts. No, my darlings. Your stomach is not down here by your belly button. Your stomach, the opening to your stomach is right up here, nestled under your rib cage at the height of your heart. In fact, the opening to your stomach from your esophagus is called the cardiac sphincter because it's way up here. Everything is much, much higher than we think of anatomically. And so I have buffers that I can take, like an antacid, like Tums. You pop the Tums, what it does is the Tums acts like a buffer and it helps to neutralize the stomach acid. Hence the buffer, neutralize the acid. The cows, let's talk about cows for a second. Cows are both delicious and disgusting. Just saying. So cows are constantly regurgitating, meaning that they are kind of burping, and we as humans aren't supposed to do this, but we've all done it, where you eat your Chipotle too fast and you burp and you get the little meaty surprise at the end. Then you re-swallow it. It's disgusting, but we've all done it. Well, that's what cows do constantly. Cows are constantly regurgitating their food so they can re-chew it. And that's because of the type of food that they are sustaining themselves. They're not really getting anything nutritional from the grass that they're eating. What is happening is the grass is fermenting, which produces sugar, which is what they then are able to live on. They're producing their own glucose. And by chewing the grass, they're breaking apart the cellulose, blah, 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 blah. Well, the problem
You
is
froze
just,
again. Could you repeat?
yeah, so was talking about cows and how cows, they regurgitate their their grass and then they re-chew it. And what they're doing is they are breaking apart the cellulose, which is fermenting into glucose. It's a whole thing. We'll get there. But the problem is with cows, just like with people, is their esophagus is not protected. And so with them constantly regurgitating, they're constantly having stomach acid burble into their esophagus. And the problem can be that it'll burn through the esophagus. So they have a naturally occurring Tums, an antacid, a buffer in their saliva. So every time they swallow, they are washing their esophagus with this buffer. And they salivate a lot. Like 25, I'd say not on average 20 to 30 gallons, guys, gallons of saliva a day. That's disgusting. Do you know how long it would take me to fill up a gallon of spit? Like weeks. They can fill up on average 25 gallons in a 24-hour period, because they're constantly having to reintroduce the buffer so that the stomach acid is not eating through the esophagus and killing them. Because again, esophagus, kind of important, but we also have the aorta, which runs right behind it. And if stomach acid eats through the aorta, you're dead before you hit the floor. So those are our buffers. They're just going to minimize the change, and they're going to help to neutralize an acidic environment. Like Tom.
Can you go back to the bases?
Do what? I'm sorry?
Can you go back to the bases? The acids and bases?
So on this, all you needed to know basically was that the word electrolytes is something that carries a charge.
Basically.
Okay, thank you.
You're very welcome. All right, this is a lot of words. Again, don't panic. I just need everyone to just stop writing for a second, because there are things on here you do not need to write. This is a handshake, how do you do, to our organic. Organic, remember, is a hydrocarbon chain. Now I'm just gonna do handshake. We got carbs, which are sugars, lipids, which are fats, proteins, which are amino acids, and then we have something called a nucleic acid, which is just what makes up their proteins that make up your DNA. Don't write any of this stuff down yet. So any of you that are furiously writing away, don't panic. All right, so let's just do a handshake. How do you do into carbohydrates? Carbohydrates are sugars. Carbs equals sugars. And the type of sugar that our body uses as currency is glucose. Glucose is a single molecule sugar. We can also have sugars that are bonded together as a disaccharide, di meaning two, sugar meaning saccharide, or we could have multiple sugar molecules bonded called a polysaccharide, many sugars. That's it. That's all I want you to know. We are going to be going into great detail with our carbohydrates when we get into nutrition class next term. We're going to be discussing how does your body break it apart? What does it turn it into? How can it restructure it? What does it do within your body? What organs are going to help to convert it? We're going to do all of that nutrition. So there's no real reason why we need to do it and repeat it here. So right now, all we need to know is sugars are carbohydrates, and glucose is the carbohydrate that our bodies use primarily for energy. Two sugars bonded together is a disaccharide. More than two sugars is a polysaccharide. So that's just the basics of our carbohydrates. And they're yummy. Things that are super high in carbohydrates are super yummy because it's sugar. Oh yeah, I'm going to get into a whole carbohydrates thing about, the whole fad diets that people are going on now. What is the one called? Keto, the keto diet. Oh Lord, not the keto diet. So dangerous. The keto diet is so insanely dangerous.
Why?
It is just, we're going to get into it in nutrition, but it is just the way that your body has to break down its reserves, and it's a mess. It causes kidney failure and liver failure, multi-system organ failure. It's not good for you. Let's just leave it at that for right now. The keto diet is super not good for you. This is just some terminology. Glyco meaning what? Sugar. Protein meaning what? Well, protein. A glycoprotein is just a sugar that has bonded with a protein. What would it be if you think like a lipo, what is it? Liposaccharide would be a fat and a sugar bonded together. Here we have, again, just definitions, you guys. That's all I'm asking for is definitions. Anna, you now know medical terminology. You're all getting very good at that. Anna means up, to build up. So anabolize, anabolic means to build something. Kata means down, under, beneath, or against. Look at that, just right off the top of my head. I can see that slide in my head. Kata means to break down. So let me give you an example. I have not eaten breakfast today. I do not eat breakfast. I very rarely eat lunch. I eat like one meal a day if I'm lucky. But my body is still using energy. My body still needs energy. Where is it getting the energy from? It is breaking down my own storage unit and converting that into energy for me to use right now. Therefore, my body right now before your eyes is in a catabolic state, a breaking down to get energy. When I eat lots of things and I eat things that have more energy than what my body needs, I build up my storage unit, anabolize. Another way I remember this is steroids, and I don't know why it just steroids. The kind of steroids that our sports people take are to make them big and strong and provide lots of muscle. What kind of steroids do our sports figures take? Anabolic steroids to build up. So that's all I want. Ana, and that's just med term, you guys, simple med term. Ana to build up, kata to break down. All right, some fats. We have 4 different categories of fats. I'm not going to test you over these 4 categories. You don't even have to write them down. All I'm going to say is that fats are used for energy, and they're well, not even converted. They're your storage units. So you have adipose, which is just the medical term for fat. Sadly, we have fat everywhere, and fat is the storage unit for energy. So do not write down any of this. I do this so you can't even see it anymore. We're not going to be going over a whole lot in the 4 classes. In fact, I'm gonna freak some of you out right now. Okay, are you ready? If you need to hold my hand, you can hold my hand. Yeah, that just happened. That just happened. You can go back and review this stuff. But honestly, like I said, we're going to be going into so much detail with our trans fats and our function and form of fats. We're going to talk about how triglycerides are made. We're going to talk about this saturated versus unsaturated. In our next chapter, we're going to talk about the lipid bilayer. So right now, I'm skipping over all of that because all we need to know right now is there are things called fats and they get stored in your body. All right, so proteins, most abundant of your body. Everything in your body is made of proteins. Right down to our core DNA and our core RNA. Everything is made up of the Lego amino acids or proteins. And they are going to have a super wide function. Some proteins are messengers. Others provide your immunity. Others still tell cells how to behave because we get a lot of different kinds of cells, right? Think about just some of the various structures in your body. You have liver cells and kidney cells and stomach cells and skin cells, and all of these cells, although they have their basic same structure, are very different jobs. And if you start having a cell that does the wrong job, bam, you have cancer. That's essentially what cancer is it's a cell that doesn't know how to do its job anymore. The cell doesn't do its job.
Out again.
Oh, you're lagging. I was telling about cells and how we have a lot of different types of cells in our bodies. And it is proteins that tell the cell how to behave. I mean, your liver cell has to behave very differently than your kidney cell. And your kidney cell has to behave very differently from your stomach cell. And so it's proteins that tell the cells how to act and what to do. If you start having cells that are going out on their own and they're like, I don't want to be functioning as a liver cell anymore, and they just start doing their own thing, bam, that's cancer. Cancer is just a bunch of cells who are not acting like they're supposed to act, and they split and proliferate very easily. So these proteins, we have specific amino acids, and proteins are made up of the 4 major elements that we talked about: carbon, oxygen, hydrogen, and nitrogen. And in fact, nitrogen, that's where our body gets the nitrogen it needs, is from the ingestion of meat. Humans, dogs are omnivores, meaning we got to get nutrients from both plant and animal sources. Cats are carnivores, meaning they are obligated to eat meat. And that's it. They're the most abundant. They're made up of amino acid, and they're made primarily of our 4 major elements. And everything right down to our DNA, RNA, all the different forms of RNA. I'm just saying words because you all are writing, and I like it when you've heard these words before. You have like transfer RNA, messenger RNA, ribosomal RNA, and all of these are just different steps in taking a recipe and making the thing. Don't write any of these down. We just know that there are 20 different Legos in the body. And again, we are going to be going into in nutrition, essential versus non-essential. Essential, you have to have them in your diet. Non-essential, you don't, because your body can bippity boppity boo them together. So we're going to be talking about all of these amino acids and which ones combine to make other things. So we have 4 different structures for our proteins, and this is kind of important because we are going to talk about this in relation to things like ribosomes and how they manipulate proteins into other structures, and DNA and RNA and all of this. So the structure of a protein is 4 layers. We have what is called the primary structure. I've got a picture that's going to show this. The secondary structure, this word here is called tertiary. That's how you say that word, tertiary. And our quaternary. So essentially, what do these things mean? Well, our primary structure is just that, right? That you take a piece of paper, the piece of paper itself is the primary structure. Then we have our secondary structure, and this is going to be where we have natural bends. The tertiary is where these bends are going to form a new shape. And then quaternary is we take a new shaped protein and combine it with another new shaped protein. All of these steps can be kind of as an analogy of origami. So I do not fold origami, I'm sorry. I don't have that ability. Some of you might. But you take a piece of paper. This is obviously not origami paper, but you get the idea. So I have my piece of paper. Actually, I'm going to get the actual piece of paper. So I have my piece of paper. This is the primary structure. And so with origami, what it is a very complicated series of folds. And so that's what I'm going to do is I am going to fold and have these natural bends. These natural bends are now the secondary structure. And when I use those bends to fold and brew, and I'm told you I'm not an origami person, but I'm now using those bends to fold it in a way that now it's still the same piece of paper, isn't it? The primary structure, look at this magic, black magic. I'm a wizard. Look at this. The piece of paper didn't change. This is the primary structure. Using the natural bends or the secondary structure to fold and fold and fold until it becomes this. This is the tertiary structure where I've taken my primary, I folded it with the secondary into a new shape called the tertiary. And then if I took another one and bloop, bonded them together, that is the definition of quaternary. And I do have some pictures that I'm going to show you here in just a second. But if I unfold this again, I unfold this protein, it's still the exact same piece of paper. I'll give you guys a minute, and then I'm going to move on to the photographs that you can see. So here we have our picture, and you can see it's exactly what I just showed you with the piece of paper.
Can you go back real quick, please?
Of course, yes, I can.
Thank you.
You're very welcome. Okay, so here I have just what I showed you with my piece of paper. Right here, I have my primary protein structure. Every one of these dots represents an amino acid. And then we have our natural bend, which would be the definition of our secondary structure. And we're going to use those bends to fold our little protein origami, which was the tertiary. And we take an origami, and we take an origami, and we bind them together. And that's the definition of quaternary. So again, all we're really looking at, you guys, is definitions. Everything in this chapter, we're just trying to define it. So our primary protein structure, our secondary is the natural bends. Our tertiary is where we've made a new shape. Quaternary, we take the new shape and we bind it and bond it together with another new shape. And I will erase that stuff so you can see it. There you
Miss
go.
Huff, so antibodies are basically proteins.
Yes. Antibodies are a protein. And basically, if you want just the most basic plain Jane explanation. So let's use COVID as an example, because it's something we've all been living with now for a year. So you have this foreign invader named COVID. And when COVID invades you, your body doesn't have any protection because we've never seen it before. Our body knows stranger danger. Stranger danger, there's somebody here who's not supposed to be here. But our body doesn't yet know how to battle it. We have this entire military inside of our bodies. And in fact, I'm going to just do a stop share right here. So we have this whole military called our immunity. And so what happens is COVID comes in, I have this immunity Groot, like an immunity deity, and his job is to search out, look for stranger danger. And so basically what happens is I get COVID and my immune system's like, I've never seen this guy before. We don't have a battle plan. And so what happens is they just launch everything. They're like, everybody go to war. We don't know who this guy is. He looks super dangerous. Everybody invade. And your immune system launches this massive attack. But your immunity group is up there and he is writing down what is working and what is not. He's making notes. And so what happens is your body, huzzah, we have been successful at killing off the COVID. But now you have antibodies. Now, if you get COVID again, you've already got the plan. You know exactly how to get rid of him. And basically, we have these little private investigators with a picture of COVID and the plan. And their whole job is to wander around your body looking for the guy on the wanted poster, COVID. And the minute that he sees it, he goes, he's on his cell phone. Oh, come on, that was funny. Because he's calling cells on the cell. You guys suck. All right, so he's on his phone. He's like, hey, I found the guy, and here we need, activity, blah, 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 blah. Immunity launches, and we are much easier able to get rid of it. All of that has to do with proteins. Without the antibody made of proteins, that's what makes up the protection and kind of the patrol for that specific stranger danger. So that's, protein. So time flies when we are having all of the fun.